All right, welcome back to CS50. This is the start of week 7. So it was actually around this time last year that I went into a bit of a rant when I was in the subway station in Harvard Square. And there was this nice lady who was clearly foreign, had never been to our subway system before. And all she wanted to do was get from Harvard Square to Park Street. Pretty reasonable goal, pretty straightforward route. And so she walked up to this device here. Blurry only in as much as I'm bad at photography. But this is these machines, if you've never used them before, that they're very high tech. You can touch the screens and interact with them and actually buy yourself a train ticket. Unfortunately, the sheer number of steps involved in buying something as simple as a one-way ticket to Park Street involves some 7+ steps. So you walk up, as I did with this woman who had turned to me or really anyone around for some help because she could not make sense of our American machines here. You walk up, you see this screen, and you've got 3 huge buttons, and the one you ultimately want is that one up there. To purchase new Charlie ticket, value, tickets, and passes, press here. Now, as an aside, and from the perspective of user interface, what is a Charlie ticket, right? We're already assuming that some outsider knows what we were talking about when we say Charlie ticket, but we can forgive that and move on. So now I'm asked what I would like to purchase. Okay, this one is admittedly pretty straightforward. So you click on the left to actually take the subway. And then you're asked for your fare here. And so that one, too, is fairly straightforward. And then you get to this point, which is a curious one in that going downtown costs neither $5, $10, nor $20. So you have to click other amount if you just want that one-way pass, which these days I think is like $1.50, $2, right? So clearly an upsell attempt here. And I think if we do the math, even $5 is not the cost of a round trip. I think it's probably $4 or so. So we clicked other amounts, this woman and I. And then you get to this, and God forbid you want to spend some triple-digit amount of money just to get to Park Street. So now you're on this screen, and you input your number. And finally, you get to this screen, which says you're buying an SV Adult, whatever the heck that is. Turns out it's single value, but who cares? The amount to pay, $4. Now I can click credit card, debit card. And long story short, dear God, it took us like 5 minutes just to buy a one-way ticket to Park Street. Now rewind to yesteryear, just when I was here, and we didn't have these fancy touch screens. We instead had these devices where you put your dollars in, and you get a T token, a metallic token, drop it in the slot, and bam, you're on your way. Like, this is not an improvement, I would wager. And yet this is representative, this kind of screen, of a horrible user interface and sort of technology gone wrong. And unfortunately, technology, and by extension computer science, too often get a bad rap for being beyond the scope of most mortals because we're so often presented with crap like this, right? Interfaces that are not optimized for the common case, which I dare say is to get on subway and go somewhere, not to go through these 7-some-odd steps. So you'll find in Problem Set 5's form this week, which will go online tomorrow as usual, you'll be asked to keep an eye out this week or to think about some piece of hardware or software, whether in subway stations, in your own life, on campus here at Harvard, that could be better. And we're going to ask you for your simply real-world human instinct as to how this software or hardware device could be better in terms of its design. Now, a recurring theme when we did this exercise for the last time last year is that there was a lot of Harvard-centric things that were pointed out. I'm sure some of you can think of various websites of which you are all too fond here within harvard.edu that could use some tinkering. So do know that we will actually group some of your feedback by Harvard and non-Harvard specific feedback so that we as a course will escalate your critiques, your informed judgments of various tools, so that hopefully collectively as a university we can rise up and present to each other interfaces that are not quite like this. Those of you who are not freshmen but lived through webmail from college.harvard.edu in years past will know that that system is no more, replaced now with Gmail. And I dare say that in particular was a recurring theme in last year's survey. And look, that problem is gone. So perhaps we as a class can similarly chip away this year. So with that rant aside, so it was a sad week over the past few days where we, of course, as a world lost Steve Jobs. And to be honest, I would say in the context of this MBTA system, I mean, one of the most amazing things Apple really has done is take technologies and make them simpler, right? Mac OS itself is not fundamentally any simpler, I would say, than Windows these days. But these phones that we have, these iPads that we have, like even technophiles have fallen in love with these things because they just make things easier. And we would be remiss in not pointing out another gentleman who unfortunately passed away last week named Dennis Ritchie, This is the author of the C language, with which you have been all too acquainted this semester. And he was also one of the co-contributors to the Unix operating system, which then gave rise to things like Linux and the like, which we've been using in this course. So there's a really nice obituary in the New York Times if you Google his name, Dennis Ritchie. But know that it's to this man to whom we owe most everything we've been talking about in this class. So with that said, what's on the horizon ahead? So problem set 5 introduces not only the world of multimedia and imagery, but also that of forensics. And part of forensics will involve understanding how things like images work. Now, it turns out that even though we look at images all day long on Facebook or just your own computer in the form of JPEGs and GIFs and PNGs, well, you can actually represent images, as you'll see in this week's piece set, fairly simply, right? If we have a trivial image that we want to represent, like a smiley face here, well, you probably know before CS50 that an image is just a bunch of dots called pixels. It's a grid horizontally and vertically of dots like this. And so in the simplest form, if all we wanted to do is implement a black and white smiley face, we could kind of do this using week 1's material. We can just arbitrarily say that the bit 1 will represent white, the bit 0 will represent black. And so if we create a file using some kind of program or editor whereby we say 11000011, we could get the top row, aka scan line, of this smiley's head there. Now, of course, images today are much more glamorous than these black and white images, but all we do to represent things like JPEGs on Facebook profiles is just more than a single bit per dot. Rather, we typically use like 24 bits per dot to represent most any color that a human could possibly see. And so you'll see that the problem set walks you through the progression from bitmaps, BMPs, which this thing here is, to JPEGs, which you then need to recover as part of the forensic challenge. But we also introduce some C and programming specific ideas. So we talked briefly in past weeks about structs, and this table here is kind of overwhelming, but what this table here represents is what you can find at the start of any bitmap file. BMP is a file format like GIF and JPEG. It's what the smiley face there was. But it turns out that it's not sufficient to just put zeros and ones in a file and say, OK, this is a BMP. Rather, file formats like the bitmap file format needs what we'll generally call metadata. It needs some hints so that programs like Photoshop and Ristretto Photo Viewer or whatever you're using to open up graphics know a little something about how to interpret those bits, right? If you just hand a program zeros and ones, it's completely out of context. It's not clear if this is a Word document, a text file, an image. So this metadata, as well as the file extension, the last 3 letters of a file name, like BMP or JPG, typically provide this information. Now, not all of this is all that interesting, but you'll see at the top that you'll see in the problem set that we do inquire about things like BI size and width and height. So information as to, well, are all of these zeros and ones that you see this wide? Are they this tall? And so forth. All of that information is hidden in here. And as an aside, the reason for these new data types, like word and dword and byte, these are actually typically used in the Windows world. When doing Windows programming, Microsoft simply has some of its own data types that there is a mapping to Linux and Unix data types like char and float and so forth. So you'll see in bmp.h, one of the files we give you this week, that we just create synonyms for these various things, for word and double word and long and bytes. So realize that we have all of the expressiveness now in C to do this. And those numbers, if not clear on the left, just show you how far into the struct, at what byte position, this particular field is. But without this information, you're kind of screwed, right? Unless you understand something about the format of a file, it's pretty much impossible to read it unless you have these hints. And similarly, for the recovery part of this problem set, where you have to recover a whole bunch of JPEGs that I accidentally deleted, just knowing a little something about this header information. This one, again, is BMPs. It's not JPEGs. But we tell you a little bit about the JPEG format so that you can similarly recover, like an investigator might, a whole bunch of images. And now in the Hacker Edition, for those interested this week, realize that this is most likely the last of our Hacker Editions, because we now kind of converge and all get onto the same page. Realize this one's actually a little more accessible than usual. What you'll do is much the same problem set, but when challenged to resize images, BMPs, to make them bigger, the Hacker Edition will also challenge you to make them smaller. And making an image smaller is actually non-obvious, whereas to make something twice as big, you can imagine conceptually just double all the pixels. Make everything twice as wide, twice as tall, and then you can just do that for any factor. But if you have to shrink an image, and for instance, you have a pixel, well, what do you do with that pixel? A pixel is a pixel. You can't shrink it. So instead, you have to throw information away if you want to shrink an image. And so one of the challenges of the Hacker Edition is to decide which pixels should you throw away. Or if something's black and something's white, should you maybe throw one of them away and just make one remaining pixel gray or something to that effect? So there's a lot of opportunities there for design. And there will also be opportunities, as usual, for office hours. But per 2 weeks ago's announcement, we're going to head across the river just this week to join the Ilab for one of its inaugural events, where we'll have the same iPad and the same approach to office hours. But upon arrival, you'll see a nice, sexy lobby like this. There'll presumably be people by then behind the glass walls there. And you'll pretty much be welcome to just spread out wherever. You can certainly bring friends from other classes. The goal is simply to hang out as a class, get questions answered by the TFs and CAs, and eat pizza and soda, which will be supplied gratefully by the iLab. All right, so Quiz 0. Also, what we'll do, I'll be there tonight. If you have questions or want to walk through your Quiz 0, you can reach out to me directly. We'll make one of the categories Quiz 0 questions tonight on q.cs50.net. And also throughout the week, if you want to walk through your quiz with one of the TFs or CAs, realize that we will make ourselves available for that. And lastly, if you're on that fence and you're here today at lecture, but you're sort of planning to head to the registrar by 5 p.m. to withdraw from CS50, please do catch me after class for a conversation if you're on that fence, because realize that we are now pretty much more than halfway through the course's problem sets and pretty much halfway through the course, so we would hate to lose you at this point. All right, now for something technical. So one of the hardest things in C of late is dealing with things like memory and pointers and malloc and free. And increasingly, will this be an opportunity to really screw up your programs and make programs that crash and segfault and core dump. But thankfully, just as we have tools to write programs, we also have tools to fix or to diagnose or debug programs. We've used, or we've said you should use, GDB thus far, the GNU debugger. But we also introduced this week a nice tool called Valgrind, whose purpose in life is to analyze your code and figure out if you've screwed up with regard to memory management. Did you accidentally leak memory? Did you accidentally go beyond the boundaries of some array? Now, the tool is imperfect. It can't necessarily perfectly test your code because, of course, anytime you run programs, you give them input. And Valgrind is not going to be able to try your program on an infinite supply of input. So it's going to do its best guess. But you'll find that it can help us find some things quite nicely. Let me go ahead and open up a file called memory.c. That's among our source code for today. And this is a pretty stupid program that's deliberately buggy in that it does the following. So let's start from the bottom. Here is my main function. Takes no command line arguments. Apparently calls a function f and then returns 0. So that looks OK. But then let's scroll upward to the f function. It returns void. It takes no arguments in. But it does, in this first line, call malloc. And just as a check, sanity check, how many bytes get malloced in this highlighted line? So 40, right? If we assume an int is 4 bytes, then 4 times 10 is, of course, 40. And then what, just to be technical, are we storing in x? An address, the address of that chunk of 40 bytes. So that's sort of from 2 weeks back. And then on the next line, unfortunately, I do something stupid. Why is this flawed, this second line of code? X bracket 10 gets 0. Yeah. Perfect. So the maximum index for this array should be 9, from 0 through 9, because I've only allocated 10 ints. So of course, this is an off by 1 error, or I'm overreaching the boundaries of my array. In the worst case, this program might crash and segfault and core dump, but not always. And that's one of the frustrating things. Often, if you just go ever so slightly outside of your memory bounds, your memory's bounds, the program might not actually crash, because the operating system is being a bit generous and is allowing you, if unofficially and in a dangerous way, to go slightly beyond your array's bounds. So in other words, this is kind of hard to catch sometimes, certainly just by visual inspection. So let's instead try this. Let me open a terminal window. Let me go ahead then and compile my code with make memory. And now if I run this program, it actually seems to be fine, right? No core dump, no segmentation fault. So at first glance, all is OK. But now instead, let me run this new program, Valgrind, and let me go ahead and run it on memory. I still need the / to say test this program here, and then hit enter. Unfortunately, whoever first wrote Valgrind decided that let's make its output a crazy mess. But if you read between the lines, you can actually see some juicy information. So let me scroll back up to the very start of this, and you'll see here's where we started. This is where I ran the command, and now we have some copyright information and stuff like that. But here's where the helpful information is. Invalid write of size 4 at such and such an address. Now, these pointers, these addresses on the left-hand side, are generally not all that useful unless we really get low level with our debugging. But it does mean that you did something wrong at that address, specifically at line 23 of what file? All right, so memory.c, right? So the output is actually quite similar to GDB. And so if I go back to line 23, which is this guy here, sure enough, Valgrind has noticed that I wrote 4 bytes erroneously there. Now, it's still up to me, the human, to determine where is my mistake. And of course, we already identified the mistake. But the program found it, even though when I ran this program, nothing appeared to be wrong. Now, lastly, this here says this actually being addressed as 0 bytes. Actually, that's OK. Let me scroll down here. And now if we go down here, leak summary, definitely lost, 40 bytes in one block. Now, this might be a much bigger program. Right now, it's pretty simple. It's only a few lines. So I can actually run Valgrind with more switches. And notice it's telling me to rerun with -- leak -check equals full to see details of leaked memory. And in fact, if I go back to my slide here, what you should generally run, even though it's a little tedious to type, is exactly this. Valgrind-v. So I'm going to try this. Valgrind-v. -v almost always means verbose for a Linux program. Some of these switches take --, not single hyphens. The convention, just FYI, is if it's a single letter switch, it's usually a single hyphen. If it's a longer word like leak, then you would actually use --. But that's just a human convention. So leak check equals full. And then I have to say a.out in general. But in the concrete case, it's the program called memory. So let me hit enter now. And oh my God, so much more flew across the screen there. But let's scroll up, and here we go. Now, because I ran it with more verbose output, and I frankly knew where to look. You would kind of have to take a few seconds to sift through this. But notice, 40 bytes in one block are definitely lost in loss record 1 of 1. I don't quite know what that means, but it looks like the bug is in a function called malloc, right? Right, so probably not, right? So you've called malloc, so let's at least chase this bug back a little further in the stack. And what was the previous function called? OK, it's probably me who screwed up. So somewhere in memory.c, line 22, a function called f was called, and somewhere in there 40 bytes were lost. Of course, in a program this small, it's pretty obvious to the reader what I did wrong, which is what? How did I lose these 40 bytes? I didn't call free, right? I should have called free at some point. And of course, this would be kind of a silly exercise to just do it now, because this is, again, kind of a bogus program. But that would be the correct fix. Just hopefully in the real world, if I'm writing some real program, there would be some useful stuff going on in between those lines. But this one is just completely wrong. Going into bracket 10 is just incorrect. So in short, unglamorous program, but a useful tool. So henceforth, anytime you write any program, whether for pset 5 or onward, that uses malloc, that uses arrays in any way, do run your program through that tool. Take a few seconds to sift through the output, and it might find a bug, frankly, before your TF does. Any questions? All right. So now we have the opportunity to start to implement, with these same fundamentals from the first half of the semester, some real-world constructs so that we can begin to solve more interesting, more challenging problems with more sophisticated tools than just an array or variable. So this is a photograph from my favorite house, Mather. And this is, of course, a stack of trays. Well, it turns out in computer science, a stack is a data structure. It's a data structure that allows you to actually store data in potentially a more useful way than, say, a simple array does. The idea of a stack, just like in the real world, is that if you have a stack of trays, there's some upsides and some downsides. One upside of a stack is that if I put something down like a tray, and then I put something else down like a tray, then I put something else down like a tray, well, it's very easy and very fast to get the most recent thing from that stack. You can just pop it off the top of the stack, so to speak. Unfortunately, a stack of trays or a stack of paper here is not the most efficient system if you instead are, for instance, queuing up for something you really want, right? It would kind of suck if you got to the Apple Store at like 5 a.m. before, or you got even earlier, to get your fancy new iPhone 3 or 4 or whatever, and the staff in blue shirts starts popping people off the queue from the back, right? That is a data structure, a bad design when it comes to selling iPhones. You would really piss off the people at the front of the line. So instead, in computer science, there's an alternative data structure that's similar in spirit. It's kind of a list of some sort, but it's called technically a queue. And a queue is first in, first out. So the acronym is FIFO, F-I-F-O. First in, first out just means if you get there first in the morning, you're going to be the first one allowed to buy that product. By contrast, a stack is the opposite, but we'll see utility of both of them. In fact, those of you familiar with HTML know that prevalent in HTML is the idea of balancing tags, having an open tag and a closed tag. And the notion of validating HTML involves checking. Did you close all of the tags that you opened? Well, you can actually use, it turns out, a stack data structure to answer questions like that if you're the W3C's validator. Now, for those for whom most of those words made no sense, not to fear, in just a couple of weeks, we'll be diving into the web programming portion of the course. But to begin to now use these data structures and solve more interesting problems, we need to be able to chain structures together. One of the biggest problems of an array is that even though it's super simple to use once you get the hang of it, and that you can go to any element in it, what can you not do easily with an array? Sorry? You can't extend it, right? You have to decide in advance if you want 10 bytes or 100 bytes or whatever it is that you're allocating. You have to decide in advance. And what happens if you decide, oh, I really need one additional element or twice as many elements? What do you have to do if you're using arrays to store your data? What's that? Yeah, you pretty much have to make a new one, copy the old data into the new one, and then free the old one. Now, we haven't done that ourselves really, but we've been using something that does. What function that we've been using since week 1 does exactly that? When it runs out of space, it allocates more, copies old into new, and then frees the old. getString, exactly. Remember, getString is a perfect example because we have no idea how long of a sentence or a paragraph some student's ever going to type when we sit down at the start of the semester to implement getString. So we have to be dynamic. We have to enable the function to grow the storage space it's using. And we've seen as of 2 weeks ago that the technique for that involves using malloc. And it turns out some other related functions like realloc and the like, but it boils down to allocating and reallocating memory. So what if there were a data structure that allowed you to have some fixed amount of memory at first, but then grow it super easily? Because the problem with using the array trick is what? If your string is this big and you need one more byte or twice as many bytes, this is a lot of work, right? You have to ask the operating system for more memory. So temporarily, you're doubling your memory footprint. Then you have to copy, as in a for or while loop, all of the old memory into the new memory. Then you have to free that memory. That's a lot of steps if the user has maybe hit one extra character. So what's an alternative? You can avoid resizing arrays in this manner by just allocating maybe 2 gigabytes of memory. Anytime the user might type something in, well, just choose a huge upper bound, 2 gigabytes. But of course, what's the obvious problem here? Right? If you just allocate an excessive amount of memory, your program at some point is just going to stop working. Or it's going to slow the computer to a crawl because it appears to be using way more memory than it should. And if you only have a couple gigabytes of RAM and your silly little program is using it when you're actually trying to do useful work with like a browser or word processor, everything will just slow to a crawl, as we've discussed. So suppose there were a structure that looked a little something more like this. Enter into the picture something called a linked list, which is pretty much what the name suggests. It is a linked list of what are generally called nodes. What's a node? For now, it's just a chunk of memory. And we can implement these little chunks by way of that C construct known as a struct. So what have we used a struct before thus far? What comes to mind? Sorry? Sudoku. So we had a struct in Sudoku to represent things like the board and the y-x location. We had something for students a couple of weeks ago where we wrapped together a student's name and ID number and house. So anytime you want to kind of clump together some related data fields and call it something new, like a student structure, you can do that. So these squares in just a moment are going to represent what we'll generically call a node. And each of these squares in this picture here stores a number, apparently an int, a 9, a 17, a 22, a 26, and a 34. And this is equivalent for the moment to an array of size 5. So I see 5 numbers, 9, 17, 22, 26, 34. So in effect, I could implement this very easily with week 2 stuff with an array of size 5. But I propose that because I've now drawn the picture in this way using arrows and not by having these numbers back to back to back, as is the case for arrays, it's going to be super easy, conceptually, to insert more numbers into this, to append them to the end, to insert them into the beginning. And there, too, is an advantage. What was really hard in an array? Remember when we had a whole bunch of people up here on the stage when we were doing sorting, and we had to move someone who was over there all the way over here? In the worst case, we had to ask everyone, can you move down? Can you move down? So just to make one swap in the worst case, with an array, we had to do like n minus 1 steps of work. But suppose the picture were like this, and suppose that in between each number was literally a gap, and there's some concept of an arrow saying the next number's over there, the next number's over there. Well, maybe we could just have squeezed that student and their number into wherever we wanted in this list. So we just need a way of linking nodes together in this way. So odds are these arrows represent what? Yeah, so pointers, right? This is how we've been generically drawing pointers on the blackboard. And so really, underneath the hood, there's some memory addresses and hexadecimal notation and all of that. But conceptually, this is a linked list. It is something like an array, but instead of having contiguous memory, your nodes, your integers, can be stored all over your computer's memory, which is great, because then you don't need to find a huge contiguous block. It can come all fragmented, like from the entirety of your RAM. And it looks like we'll be able to more easily insert numbers into these lists because we can just temporarily move one of those arrows, slot someone else and another number in there, and then fix what the arrows are pointing at. So let's just take a look at what this might look like. I'm going to go ahead and open a file called, let's say, list1.h. And I'll propose this as the container for one of these things called nodes. So we've seen this syntax before, even though we haven't written it ourselves all that much. Typedef does what? Right, if you kind of want to be astute, you can just say, well, it defines a type. Well, what is that? It makes a synonym. One type is a synonym for something else. So let's see what this means here. So we see the keyword struct, and we see the word node. So gedit's being friendly and highlighting all of the C-specific words. So typedef and struct are C keywords. Node is just something I made up. It could be called foo, but by convention, we call these things nodes. And then what composes a node? What is in one of those rectangles? Well, two things. One is an int, and I can arbitrarily call it n, but I could call it anything I want. But then the curious feature is the second thing, the bottom half of this picture here. So for instance, here's n, the number 9. This field here, which I'm apparently going to call next, what is that? Well, if it's an arrow, that suggests pictorially that it's a pointer. How do we write a pointer? Well, with a star somehow. But what is this a pointer to? Well, it's a pointer to the same kind of structure. So we say struct node star, and then we choose an arbitrary word for this arrow. And I'll call it next, just to imply that it's always pointing to the next object. And then down here, I have the word node again, which feels a little redundant. And it is in some sense. So at the end of this statement is the word node. That relates to the typedef. So what this word and this word together mean is henceforth call this whole thing more succinctly node. But remember that C is not so generous. It doesn't look ahead in your code. And so we kind of have a problem. Because if I want to create this pointer inside of one of these structures to another such structure, does the word node exist at this point in time? Not really, right? The word node is literally declared here. Well, wait a minute. You also said node here. But this is, again, just because. I need temporarily a name so that I can refer to myself inside of this structure. So long story short, struct node creates this thing. And then the combination of typedef and node here, rename it more succinctly from struct node to just node. Why? Why this complexity? Frankly, it's just tedious typing struct node, struct node, struct node all over the place. So now we can just call it node thanks to typedef. But if that's a little unclear syntactically, that's fine for now. Just take for granted that it makes one of these rectangles possible. So how do we now start to manipulate these things? Well, let's rewind just a moment to an example that we already looked at in the past. Recall this thing from a couple of weeks ago. This was a structure that we used to define a student. And there's one syntactic difference. What is fundamentally different about this is there's no word here to the right of struct. Why would I not need to say type def struct student using the logic from a moment ago? Exactly, and let me tweak the word. I don't mention student inside of the struct, so I don't need a temporary word there. But I could put this here. But again, just as a matter of style, because I'm not using struct student anywhere, I might as well make it more succinct. I do need to say struct, and it's in red because it is an important keyword here. But I don't need to say student up here unless I'm going to refer to a student internally. And this hopefully makes a little bit of intuitive sense, right? If I'm a student object, there should fundamentally, in the real world and in programming, be no notion of next inside of a student object, right? I shouldn't, as a human, have some kind of data remembrance of someone to the left of me. So again, we don't need a pointer there. But we do have 2 pointers for name and house. So how did we use this? Well, recall students structs1.c, which we looked at briefly a while ago. And this was just a simple example where we created a bunch of structs of type student. We then got the user's ID and the user's name and their house. And then we scrolled down and just yelled out, so-and-so is in Mather, if they were in Mather. So recall this was from a couple weeks ago, and there's only a couple important takeaways for now. For now, recall that this is how we declare an array of students. And for those with prior programming experience, class means like a class of students, not a class of objects. So student class gives me an array called class of student student structures here. So what goes on here, this was the new syntax. If I want to update the ith student's ID number, I use the dot syntax. If I want to update the ith student's name, I use the dot syntax. And if I want to use update the ith student's house, dot syntax. That was new. Then this was kind of old school stuff, stir comp for string comparison. What was I comparing? I was comparing their house against literally the word Mather in double quotes. And then this was important here. I did need to, for good measure, call free on house and name. Why? Because what? Sorry? Because I stored it, but how did I get those strings, name and house? So I used getString. And even though this was kind of some garbage we used to kind of brush under the rug, this was kind of a flaw in our previous programs for several weeks, we revealed a couple weeks ago that getString all this time has, of course, been using malloc. And so now anytime you use malloc, whether directly or indirectly, you must free that memory. Otherwise, Valgrind, this tool I showed a moment ago, that would actually catch. If you ran Valgrind, in fact, on most of your prior programs that used getString from earlier in the semester, almost all of them would be buggy in that they would all have some memory leak. All right, but that's OK. That was deliberate, and those were the so-called training wheels that are now off. So let's just do one modification of this to kind of tie this together also to this week's problem set 5. So this is structs2.c. It's almost identical, but I thought it would be kind of neat to stop writing programs that take in input and then produce output and then lose that output forever. It would kind of be nice if our program, for instance, could store permanently the names and IDs and names of all of the students we type in, right? If we want to approximate the idea of a database, a server that stores information long term, well, it'd be kind of nice if I could use these same ideas now and start saving my work to disk. Just like we take for granted in Microsoft Word or the like, the ability to save, let's do that ourselves. So here is exactly the same code. Give me an array of student structs, populate them using getInt and getString and getString. But down here, go ahead and say whoever's in Mather just to be cute. But now, let's save these students to disk, which just means save a file. So how might we do this? So we could do this in any number of ways. Microsoft back in the day decided that a .doc format, DOC, is going to store your essay and your boldfacing and your table of contents in a certain way. Similarly, we as programmers here have to decide how are we going to store something like a student ID and name and house, perhaps for multiple people in a file. So you could actually do this in a bunch of ways, but we decided totally arbitrarily that we're just going to store these IDs, names, and house one per line in a text file, just so we can see it. But this is, of course, a very unsophisticated approach, but it will allow us to write files to disk. So let's see this. The very first line of interest is this thing here. So fopen, you might guess, is file open. And we've not had to use this ourselves unless you already dove into problem set 5. But as the name suggests, it opens a file. What's the name of that file going to be? Arbitrarily, I called it database. It could be called foo, but again, I chose database. And then just take a guess. What does quote unquote W mean? So it means write. So it means write this file as opposed to reading it. So you can actually use the same fopen function to read files in, but for today we'll just do it with W. As an aside, you might see in various books or tutorials people saying WB for write binary or write ASCII. Realize that on the appliance and on most modern systems, it suffices just to say R or W. You don't need to worry about the B, just FYI. So why do I check for this? If FP, which is just generic notation for file pointer, if it equals null, when might something go wrong related to writing a file to disk? Why might fopen, just conjecture, return null? Sorry? So database is missing. Maybe that file doesn't exist. In this case, that's going to be OK, because what's nice about fopen is if you're writing a file and it doesn't exist, it will create it for you. But a good thought. That would be the answer if we were trying to read it back in, certainly. Yeah. Yeah, so if your disk is full, right? If your hard drive is just overflowing with other files and you just don't have enough space for any new file, fopen could return null. Other, maybe more technical problem? If you've done something stupid or accidentally, like change the permissions on some folder, or you're in some folder on the system that doesn't belong to you, it's someone else's My Documents folder, for instance, well, fopen might return null in that case too. So in short, if you lack the ability to write a file, you're just going to get back null. But what is it you're going to get back? Well, FP is of type file, and it is in all caps just because someone decided to make it that way. And it turns out a file structure, F-I-L-E in all caps, is some kind of structure, not unlike conceptually a student structure, inside of which is a bunch of stuff. And that stuff is generally hidden from us. But you can think of a file kind of like a cassette tape, if you even remember these things. A cassette tape, of course, has a whole bunch of tape inside. And when you play a song on a cassette tape, these two things turn and the tape physically moves. A file on a computer system obviously has no tape, but conceptually you read and write it in the same way. When you open a file with fopen, it's like taking out a cassette tape and starting at the beginning of that tape. And as you start to read from the cassette tape or read from the file, it's like advancing the reading head, the cursor, so to speak, or the file position indicator, so to speak, on that file. And if you write to a file, similarly that happens. Now this is relevant because in problem set 5, one of the challenges is to enlarge a bitmap file. So you have to take a pixel and double it or triple it and so forth. So realize that one of the challenges that arises in problem set 5 is, well, if a file is being read from start to end, just like a cassette tape, well, what if you need to kind of rewind the tape and go back and reprint those same pixels, re-output those same pixels? Well, there's functions like fseek, file seek, which can help you do this. There's frewind, although that's typically overkill. But there's other ways altogether, as Tommy discussed in the walkthrough involving arrays and just remembering some of those bits. But in short, for now, this is a pointer to a file structure, and it's not clear to us just yet what's actually in that file. I accidentally quit there, so let me go back to structs2.c, and we'll finish this story. So how do you write to this file? Well, if I get as far as here, inside of this if condition, the file opened OK, and I'm good to go to write. So how do I write to a file? It's actually pretty familiar. So you don't use printf, use fprintf for file printf. The first argument is apparently a pointer to the thing that you want to write to. And what are the second and third arguments, apparently? It's pretty much identical to printf, right? It's the format string. What do you want to write? And what do you want to substitute in for any placeholders? So apparently I'm going to write integer followed by a new line, a string, new line, string, new line. And I'm going to plug in each of these students' IDs, names, and houses. Then I'm going to close my file with fclose as file close. Then I'm going to go back and free the student's name and house. But one question, I don't free the student's ID number. Why? I don't free ID. It's not a string, it's an int, and we did not allocate that integer with malloc. It was just there inside of the struct, recall. So let's see what the end result here. So this is structs2.c. Let me go ahead and make structs2. OK, it seemed to compile OK. Let me go ahead and run this now. So run structs2, enter student's ID, let's say Matt Kirkland, student's ID, let's say Rob Kirkland, student's ID 3, David Mather. So it still says David is in Mather, but then nothing. But if I do ls now, there's a whole bunch of code from today as well as this file database. So let me go ahead and run gedit on database, enter. And voila, we've just created this file. Again, so primitive, this format, right? This is not what a Word document looks like inside, but it is our own proprietary file format, just as Bitmap and JPEG have their own file formats. And ours, too, is in just ASCII text, which might not be sufficient if we want to store something like an ID photo, but at least we now have one way of expressing ourselves persistently by writing these things to disk. And it remains then to use these same fundamentals to start linking things together in an interesting way. Well, let's go ahead and take our 5-minute break now, and then we'll return to that. All right. So we are back. Linked lists are much more exciting when we actually make a mess of them with actual humans. So if we could indulge, are 8 people willing to volunteer on center stage? Have to be comfy on camera. OK, let me decide this randomly. Who's going to come up? OK, here we go. How about you 2, 3, 4, 5, 6? I'm liking this side of the room. 7, 8. Come on up. All right, you lost your chance. All right, come on up, and we are going to hand you the same numbers we see here on the screen. So you'll be number 9. And if you want to go in our usual spot over there, welcome 17. Welcome 22. Welcome 20. Uh-oh. OK, 26. We'll fix the slide to make this consistent with reality. 34. You can be first. You can be pointer. You can be predecessor pointer. Very dramatic. All right. So slight bug. Oh, and this is an image too, isn't it? May I see 20? Who did I get wrong? 29? OK, debugging. One moment, please. Fixed. OK. So that's 26. OK, so here we have a linked list. And let's ignore for the moment how we got to this point already. Let's just assume that we're fast forward 10 minutes mentally, and we already have the ability to create linked lists. And here is the state of our world at this moment. And actually, let's pop out, if you don't mind, pointer and predecessor pointer, if you could be here in the heap for just a moment. So first, this is good. And now this is the point at which we need to really mimic this picture. If you could somewhat awkwardly with your left hand point at the next person. Except for 34, where I would point down with your left hand. OK, so now we have implemented a linked list with humans. So what's going on here? So first of all, each of these, oh, you still have to point. Each of these structures has 2 things inside of the struct. We have an integer, like the number 9, and then we also have a left arm known as next, which is the pointer. So each of these humans represents a struct at this point with those 2 fields for a total of, little check, how many bytes does each person represent? How many bytes? 8, right? So 4 bytes for the int and 4 bytes for the pointer. So each of these rectangles is 8 bytes on a system like the appliance. Now, first is a little special. So first, what's your name? Lisa is special in that she does not have an integer. She is only a pointer. And so the reason for her being drawn as a smaller rectangle up there is that she's only 4 bytes. But Lisa is super important because without Lisa, we're going to forget completely where this whole linked list is. And without Lisa, we would have a whole huge memory leak if we allocated all of these nodes but didn't remember where the first of those nodes is. So for now, Lisa is special. She's a pointer. And Lisa really is our linked list. So we've had arrays before, and we've had names of arrays, which are really just the addresses, as we've seen. And so Lisa is sort of the equivalent of that. The only piece of data we have to keep around in memory to remember where the entirety of our linked list is the first person, a pointer to the start of the list. And now all of these guys are fundamentally the same. They're in complete structures, except for 34, who apparently is pointing at the ground because that's the end of the list. So that's probably going to represent what when pointing down? So null. We need a special value to say, there's no one else to the left. So when pointing down, this represents storing the null pointer, all zeros in that pointer field. OK, so the first challenge at hand, and we'll make use of you. You don't technically have to keep standing there like that. We'll use you in a moment. OK, so let's go ahead and try inserting at the end. So we need the number 55. And actually, let me changing. Let me steal pointer. Can you take on the role of 55? So what's your name?
Lucas.
Lucas. Malloc Lucas, right? So now we have another 8 bytes inside of which we can put the number 55. And now let's figure out how to insert Lucas into this list. And actually, what's your name again? Joseph. Oh, OK. And I'll take that too. So Joseph, if you want to kind of take charge here and explain just in real human terms, how do we insert 55 into our linked list? If you want to go ahead and make the insertion. Sure. And let me give you this, if this is on, just to explain what it is you're doing here.
OK, so I guess you take him to the beginning of the list, and you know this is where the list starts.
OK.
You go down through each pointer to find the end of the list, and then end up here.
OK, good. So we found the so-called tail of the list. And then what did you do?
Then you insert him there.
OK, so let's push a little harder on what it means to insert into the list. So you put him there, but
So you take the pointer of the last element in the list and put.
OK, excellent. And where should his left hand be pointing?
To the ground.
OK, good. So, and this is actually quite important. Just because you've malloced a node, a structure, put in the number 55, you also have to change what the default next value is, because just as with local variables, if you just malloc a node and then put 55 there, what's going to be inside of the other 4 bytes called next? It's just some garbage value. And that's really bad in the context of pointers, because if you follow a garbage value as a pointer, you're going to end up in some crazy place in memory, and the odds are that you're going to segfault or core dump. So that was really good. So now we have 55 at the right position. 34 is pointing at 55. Let's now try to do a little something else with this list. Suppose we instead now wanted to insert the number 5. So I need to malloc one more volunteer, please. OK, come on up. Malloc number 5. What's your name? Emmy. OK, so Emmy's been malloced here. We're going to need you again with the mic to handle our insertion at the head of the list, and consider now what is fundamentally different about insertion at the head of the list. And the reason, of course, that we're doing head and tail is because we're trying to keep the list sorted, which we've tried to do with arrays in the past. All right? Go ahead.
So now you have her.
Oh, and talk as close as you can.
Okay. So you have her someplace in memory.
OK.
And you want the first person to point to her, and her to point to the next person.
OK, good. And now, even though as humans, they did have to kind of shuffle left and right to make room for each other, in memory, because each of these nodes is at some arbitrary location in memory, as determined by malloc, notice what did not have to happen was 19, 17, 22, 26, 34, and 55 did not have to move, right? If they did have to move, the running time of insert would not be constant time. It instead would have been what? Big O of n, right? In the worst case, if we had to move everyone over by one spot in memory, which we would have had to do in an array, it's big O of n. But instead, insertion is big O of 1, constant time, because all we have to do is go right to the start of the list, and we know where Lisa is, because she, again, is the special pointer that we always keep around. And even though we had to do a couple things like point her at 5 and 5 at 9, well, that's still 2, 3 steps. It's a finite number. It's constant. So that was a really fast operation. By contrast, what was insertion at the tail of the list?
The same thing.
Well, big O of?
Big O of, well, you had to go through every pointer.
OK, we had to go through every pointer, so big O of n. Exactly, so big O of n. So let's see now what happens if we make this a little trickier. I have one more node, so I need to malloc one last volunteer, number 20. Ansel, come on up. And so we've malloced another node, and take it away. He belongs in the middle. And explain for the audience, if you could, how we find his location, because it's not as simple as the tail or the head this time.
OK, well, in the middle as in?
Well, so in sorted order. So,
Sorted order. Okay.
yes, and you can walk in front if you need to see the actual numbers.
OK, so what's your name?
You weren't expecting it to be this involved, were you, in this demo?
But so you go to first pointer, follow it to the next value, compare the value.
Good.
Then, if it's greater than the value in the first element,
OK.
you point to the second one, compare those.
Good. Please just watch where you're walking. OK. OK. And good. And so now, how many pointers need to be updated?
Oh, shoot. So however many, whatever element that is.
Good. OK, well, actually, let's do that. Can we pop Ansel out for just a moment? And 17, if you could keep pointing to 22. So just super deliberately now what needs to be updated in the way of left hands to insert Ansel in the right location.
Okay, so he has to point to Hansel.
Okay,
He has
good.
to point to her.
Good. Bug. So you just broke our linked list. How and why? And someone else can answer this. I don't want to put you too much on the spot. What was the bug in that? Right, so you have to point Ansel at 22 first, because otherwise what happened? When we updated 17 to point to Ansel, number 20, we now have lost a pointer, namely where did 22 go? Where did 26 go? We have a dangling reference. We've orphaned, frankly, those 4 people there. So this is an example of perfectly memory leak. So well done. So let's fix.
So now you point.
OK, Ansel points to 22, and 17 points to 20, and voila. Whew. OK, so that was a lot of work, but incredibly important now, the order of operations. So let's hold that pause for just a moment, and let's see if we can't round out just a couple of more, because I promise you it's a lot more interesting to look at humans do this than actual C code. So suppose we wanted to remove the tail of the list. Suppose that we said we needed to chop off number 55, or we want to remove the largest element from the list. Where are we going with this? Well, you can imagine now, if we have the ability to represent a dynamic length of a list that's more interesting, more dynamic than an array, we can start to implement that idea of like a stack of trays or a queue in something like a line outside the Apple Store. So suppose the goal now is to remove the highest numbered person, 55. What needs to be updated?
Okay, so you can just point her to the ground.
Good.
Free him.
OK, good. But what did – OK, so that's good. But technically, we ran the risk there of doing what again? We technically might have lost 8 bytes of memory because we pointed 34 down, which means, OK, well, where was 55? So we at least need – and I can help out here – we at least need to either invoke me, like a temporary variable, and I point at 55. Now 34 can point again at the ground. And then what do we free? We free this pointer, which is still pointing at the same node. Or what could you also do? Rather than – right, you could free 55 first. There's nothing bad about freeing a node that's being pointed at by someone else, so long as you immediately thereafter lower 34's hand. So either you can do it with a temporary variable or just do it in the right order. And lastly, if we want to actually update, say, the head of the list such that it looks like this, we want to remove number 5. Can I put pressure on you one last time to get this one right with no memory leaks?
Okay, so we want to remove 5?
We want to remove 5.
Okay. So
what needs to happen?
okay, first, okay, involve the temporary pointer.
Okay.
Point at 5.
OK. Oh, let's talk a little closer to the mic.
Okay, point at 5.
Good.
Point her at whatever number that is 9. And then you can free the pointer.
Excellent. So if we could, a big round of applause for these guys. This was not easy. Very nicely done. You guys you can head out to Rob there. Thank you so much. So now let us make linked lists look much less exciting with actual code, just to get a sense of what happened here and how to start thinking about this. You'll find that we've implemented all of that now for you, and you'll find this will be particularly useful for problem set 6. One of the challenges in problem set 6, recall, from a much earlier teaser, is to implement the fastest spell checker possible. Now, at first glance, this might seem a little mundane, but it gets hard when the list of words, the list of English words you're going to be handed is like 150,000 words long, and you're going to need to somehow read those in from a file, much like you're doing already with problem set 5 this week. But then you're going to have to somehow lay out all 150,000 of those words in memory so that lookups, spell checking, is incredibly fast. Now, the simplest implementation of a dictionary is actually pretty simple, right? You allocate enough RAM, enough bytes to fit all 150,000 words, and you just load them up into a huge array, right? One word after another, much like argv contains all of the command line arguments. It's not hard to implement a spell checker or a dictionary if you just put everything in an array. But what would be the runtime? What would be the big O notation for spell checking a single word, if that's your implementation? Big O of... So if you have n words, or 150,000 words, let's genericize it as n. Big O of what is the running time of spell check in the implementation that uses an array? right? It's n, right? It might be n over 2 on average, but we always get rid of constant factors. So big O of n is actually pretty fast compared to some of the horrible sorting algorithms we played with, right? Bubble sort, selection sort. Those things really underperformed compared to things like merge sort. But relatively speaking, even linear time is something that you might want to avoid. What's an example of a running time that we saw that was actually better than linear? And what algorithm did we see that in? Yeah, so binary search, right? This divide and conquer approach where we counted students or we found numbers behind pieces of paper on the board. So log n is even better. But now the holy grail this week and next is going to completely one-up ourselves and try to achieve constant time, whereby even if you have 150,000 words, the challenge ultimately in problem set 6 is going to be to get as close as possible to instantaneous lookups. No n, no log n, nothing other than constant time. Now, we're almost going to be able to get there. But you'll see that it's going to require some ingenuity. Among them, tricks like linked lists and something called hash tables or tries and trees and the like. So more on that to come. But for now, let's take a step toward it. So here is list1.h. And here again is, just to be clear, the structure that each of these guys, except Lisa, represented a moment ago. Each of them had an int n held up on paper. Each of them had a left hand called next. And now those were our 8 bytes that each of these guys represented. Now I'm going to go ahead and open up list1.c. And we won't dwell on all of the minutia here, because it can actually, frankly, unless you kind of work through it slowly, it's very easy to get lost. But let's take a look first at what this thing does. Let me go into a terminal window. Let me do make list1. And let me go ahead now and run list1. And you'll see that just so that this is interesting, I created sort of a poor man's menu here, whereby it just waits for you at this command prompt to either type in delete, find, insert, or traverse. All of those should be self-explanatory, except traverse just means start at the beginning of your list and just print out all of the numbers. That's all we mean there. So I just needed a little menu because I wanted to implement functions called delete, find, insert, and traverse. So what do I want to do here? Let me move this slightly over and do delete. Well, there's no number to delete, so the list is empty. So let's actually start with insert. I hit 3 for insert. What number do I want to insert? I'll insert the number 5, just like we started with there. So now, just to see what's going on, every time you execute a command, I wrote the program in such a way that it just tells you, it reminds you what the current list is from left to right, just like our humans. So let's do another one. Insert. I'm going to insert, let's do the exact same numbers. So I had 5 in there before. Let's also put in the number 17. That was among our numbers. Let me do another insert, this time for 9. So those are 3 of the numbers we had. And notice now that the program is, at the moment, smart enough to actually insert at the right location. 55 is going to go all the way at the end there. And I can continue this. And I could insert all of the same numbers that we had up here on stage. So now let's peel back the implementation and see how this is working. So first, what do I need at the top of this program? So I've got a bunch of includes. We haven't seen all of these before, but I'll wave my hands at the new one there, unistandard.h, and just point out that, one, I'm including my own file, and that has the type def we just saw. And I also have a global variable. I could avoid this, because remember, we've generally preached that global variables are bad. But when you're implementing a program, as in this case, whose sole purpose in life is to do one thing, implement a linked list, it's pretty reasonable in this scenario to have a global variable. Just like in the game of 15, we had a big global variable there called g, because the whole program was dedicated to the game. We might as well have one global rather than pass the same pointer around again and again. So here is essentially, I could, to be clever, just rename this, Lisa, right? So Lisa represented this pointer here. So she's 4 bytes, which is implied by the fact that there's a star there. Even though a node is 8 bytes, remember that every pointer is 4 bytes. So this variable now represents Lisa, but I'll go back to the global variable here called first. And that was the piece of paper Lisa was holding up. So that's Lisa, and she's initialized to null. And this, too, is important. If you don't initialize Lisa, or the head of your linked list, to null, you're going to assume that whatever garbage value was in Lisa's left hand is an actual node. And if you follow that pointer, bad things are going to happen if no one existed to the left of Lisa. So this is incredibly important now to always initialize your pointers to some known value, for instance, null. Now, I've got some function prototypes, and I promised that those things would exist. Let's scroll down to main. So main, here's how I implemented the menu. As we've done in the past, I have a do-while loop, and that's how I keep prompting the user again and again. Here's just the menu. It's kind of formatted in this way for just aesthetic purposes. As an aside, if you've never known this, if you have a really long string that you want to print with printf, and you don't want it to wrap and wrap and wrap around, you can actually close the quotes, as I did here, and then just hit enter, and then put multiple quoted strings on each line with no other punctuation, no commas, anything, and they'll be automatically concatenated together. They'll be attached to one another automatically. It's just a trick for keeping your code a little prettier. So here's where I say command. I use a getInt call to get the command. Then I have a switch statement, and this is nice and clean because if the user types in 1, I call delete, 2, find, and so forth. So all of that is kind of older constructs. And then I have this trick here. If the user types in 0, that's how they would quit. Now, this is not the most friendly interface. It'd be nice if I supported Q for quit and the like, but that's really not the goal of this program. Let's focus instead on the linked list. So notice here that at the very end of main, I already had the foresight to free this list. And so if you assume that the user might start inserting nodes, that means that you're going to call malloc a whole bunch of times. So in my main function, before I quit, I want to make sure to free any memory that's been allocated by this program. Now, how does this work? We'll come back to this. But here, I have a temporary pointer. That was me. I was this temporary variable in the story. I'm pointing at the same thing Lisa's pointing at. So this is actually important. Lisa a moment ago, so Lisa took her paper, but suppose this was Lisa here that said first. So if I say pointer gets first, what am I pointing to? Here's first. OK. So here's Lisa. Here's me. What am I pointing to when we do this highlighted line of code? Pointer gets first. There's kind of two answers. Am I pointing to Lisa? Or am I pointing to whatever she's pointing at? So I'm actually pointing to whatever she's pointing at. Because consider what's going on here. What is first? Well, first is a pointer. And it's declared up here. Well, what does that represent? Even though we refer to this thing as Lisa, Lisa contains a value. Her left hand represented that value. So if I say pointer gets first, that means do exactly what Lisa's doing. Put inside of your 4 bytes exactly the address that Lisa was storing. And that happened to be the address of like number 5 or number 9, whoever was there at that point in time. So I'm going to actually be pointing at the exact same thing that Lisa is, but not at Lisa herself. So what then happens? Well, this is just a trick. And this is very common in linked lists and data structures where you need to free a bunch of stuff again and again. I have a while loop, and I'm saying while my pointer is not null. So while I'm pointing at a legitimate person, and you can see how this story ends, right? If I get to the end of the list and then I follow the pointer, eventually I, the temporary variable, will be pointing at the ground also, null. So that's when that loop will stop. And for now, this is what's going on when you needed to remember, before freeing something, how to keep track with fingers in code here. So I butchered that sentence. What I mean here is this. This line of code obviously frees a pointer. It frees a struct. So what are these two doing? Well, there's one new piece of syntax here. So when I am standing here and I am pointing at, say, the first node in the list, number 5, I am then going to go ahead and create a duplicate here, pred pointer, which is also, whoops, I have it here. These two are temporarily equivalent. So I'm pointing, pointer is at this guy here, say number 5. Pred pointer at the moment is also pointing to number 5. But what does this line of code then do? This is the only new one. Pointer, who's currently pointing at 5, gets pointer arrow next. So that's saying go to this guy, follow his left hand, and point at whoever was to his left, which in this case I think was the number 9. So in short, this piece of code here, and it's nice that the syntax actually uses an arrow, says update pointer to be equal to whatever it's already pointing at, which is pointer, but follow that next field, follow the arrow. So this one line of code is just my way of, again, having a temporary variable pointing at this person. And if I want to point at the next one, I need to follow that arrow to 9, follow that arrow again and again and again. And if I keep doing that, remember that 55's left hand was pointing down. So as soon as I follow that arrow, my own PTR variable is also going to be null. Now, why did I keep pred pointer around? Well, you could do this in different ways, but I needed to make sure that just because I advance to the next pointer, I need to make sure that I don't orphan the previous person. I need to remember them because I need to advance this pointer and then delete, or rather free, this person. Suppose I did the order of operations differently. Suppose I did this: free pointer, which feels very reasonable, and then do pointer gets pointer next. I mean, frankly, this is kind of intuitively, I think, much more straightforward. Free what you're pointing at, and then update yourself to the next pointer, and then repeat. But why is this bad? Because I already, exactly. If as soon as you call free on a pointer and thus a struct, you are not allowed to touch that memory anymore, because it's possible the OS, even though it's just between two lines of code, it's possible the operating system might need that chunk of memory immediately allocated to someone else, and voila, you've just now followed a pointer that's no longer your own. In reality, that's not quite how the story is going to go, but the idea is the same. Once you have freed memory, it is no longer yours to touch. It could, in fact, be reclaimed and used in some other form. So that's why, frankly, we have to kind of jump through these hoops and, frankly, make the code more complex and harder to understand. But all we're doing really is implementing these idea of temporary fingers pointing at these nodes and only freeing them once we get the ordering right. But for now, let me wave my hand at that, and let's focus on, say, insert. So insert is actually a little long, but we'll look at just a couple cases. Right? And so this is where pointers get interesting, but realize we're providing this code for a reason, so you don't need to implement it all from scratch. So how do you go about inserting a number, like the number 5 or 9 or 55 or whatever, into the list? So first, I need a node. So I'm going to call malloc, and I need as much RAM as is the size of a node. And then I store that address of memory in new pointer. And then I just do a sanity check. If new pointer is null, I'm just going to return, because I'm obviously out of memory. Something went wrong. Can't proceed. So that's what creates an empty human on stage with no number and no pointer just yet. All right, now I initialize the node. Number to insert. Well, I'm just using getInt. And here's how, given a new pointer, so given a human on stage, here's how I update his or her n field, the integer. And then I initialize the next field to null. So let me just point out one thing syntactically. This is kind of new, this arrow notation. And remember before when we've used structs, we use the dot notation. Why am I not using the dot notation here for new pointer? Even though I claim new pointer is, at the moment, because I've called malloc, this is what our picture looks like. This is our node. This is n. This is next. This is new pointer. And if we could try our camera trick. So, whoops, didn't see that. So this is what just happened. When I call malloc, I get this. When I store the return value of malloc in new pointer, I get this picture. And so this is what's going on in memory right now. So when I call getInt with my next line of code, and suppose I type in the number 5, what happens? Well, new pointer, arrow n, gets the number 5. And then this I'm initializing to null, so I'll just write null in there. But the question I posed was this: if this is a struct, why am I not using the dot notation as I did earlier today and 2 weeks ago? Yeah, so it's an address. So new pointer is not a struct at this moment in time. If I had a struct, it would be like this: node, a new node. That is a struct. Because recall, we declared node as a data type. So struct a new node. That is something that I could do this notation on. A new node dot n gets 1, 2, 3. And then a new node dot next gets null. But I didn't do that because new pointer is what? Well, it's an address. So just like this picture suggests, it's a pointer pointing at a struct. So I need to not use the dot because, look, there is no n or next field in this value. I have to follow the arrow to get here. But to reveal that the syntax is actually the same, in previous lectures, how did we start at a pointer and then go there? What was the syntax for saying, here's a pointer, go there? Yeah, so star. So you know what? This arrow notation we're seeing now is actually equivalent to writing this. So this is exactly equivalent. So it's saying, here's new pointer, go there, thanks to the star notation. And once you're there, you can use the old school dot notation. So that begs the question, why the arrow? Why not just write this code like this? This is more of this syntactic sugar, right? It's the same effect, But frankly, I would claim that this is just a little more readable. In fact, it kind of mirrors our idea of pictures much more effectively than star and parentheses and dot. But these are equivalent. And the commentary here is just to reveal that they're doing nothing new. It's just a new piece of syntax. All right, so now we've initialized the null with both an n, like 5, and null. Now I'm going to do the following. So this case is easy. Suppose the list is empty. Suppose Lisa's just standing up here awkwardly. She's initialized to null, so her hands are like this. And there is no linked list, like Lisa is null. Well, this is actually the easiest case to handle because I malloc someone from the audience. I insert the number 5 into his or her n field. And then what do I do with their next field? Initialize it to null. And then what do I do with Lisa? Just point Lisa's next field, or rather point Lisa. She is a pointer at that node. So this scenario here, check for empty list, we didn't mimic this on stage, but this is by far the easiest scenario. If Lisa is not pointing at anything already, and we've just malloced a new node, ergo we have a brand new linked list, just point Lisa at that node. Now, it gets a little trickier if the list belongs elsewhere. We have to do a little thinking now. Suppose that first is not null, so Lisa is actually pointing at a node. But suppose that the new node's n field is less than the first node's n field. So suppose the list has the number 5 in it, and I'm inserting the number 1. Just conceptually, to keep these things in sorted order, I need to put someone between Lisa and that first node, update Lisa to point to this new thing, number 1, and update 1 to point to 5. So how do I do this? Well, first, just notice our syntax here. I'm using my arrow notation to check those values of n. So if the new node's n is less than the first node's n, what do? Well, new pointer next. So here I can avoid temporary storage. If I am now the number 1 and I belong here, I can just steal whatever Lisa's already pointing at. So I'm the new node 1. I want to point my left hand at whatever Lisa's already pointing at. So at this point in the story, both she and I are pointing at number 5. But now who do I have to update to finish the story? I just say, Lisa, like point your left hand not at 5 anymore, point it at number 1. And so now we have an insertion at the list's head. So if we scroll down further, unfortunately, it gets a little messier. And we had the advantage before of using humans who could just kind of walk back and forth over stage. But suffice it to say that these lines of code here, in that there is a loop involved here, there is an equality test. We're checking for duplicate values now. And we're also checking whether something is less than or greater than. So here's a greater than side. Long story short, the remainder of this function is what implements all of these humans working together, where we had maybe a temporary variable. We walked down the list, looked for the right spot, inserted the node into that location, kept track of the left hands to make sure we got the ordering right. And this is definitely more complex than those first scenarios, but that's fine for now. The takeaway ultimately for today is that the basics have sunk in. Any questions on linked lists? They will recur. This is not the last time. Well, with that said, why don't we end on this slide, and we'll see you on Wednesday.